Hello everyone and welcome to false topographic perception phenomena and its correction part 2, in which we are going to discuss much more about the corrections of FTPP. In the first part we have discussed what is exactly FTPP and in which situations we observe FTPP. So, here now we are going to see in further details. And this is what the arrangement which I was discussing in normal remote sensing images of from remote sensing satellites which are being acquired from sun synchronous satellites or near polar orbiting satellites, which are typical remote sensing satellite. So, here is the sensor which is shown here, and the sun position is this one and north is here. Now, when this arrangement is there, then you can also have a feeling about what I was discussing about sun elevation angle. And generally in morning hours, that means between 9:30 to 10:30, when the images are acquired from sun synchronous satellites, this angle, that is this sun elevation angle, is around 45 degree. This is what it is shown in this figure also. And then we are having another angle which is more important here is the sun azimuth angle, that is the with reference to. So, in this situation the sun is shown from roughly from the southeast quadrant, and if observer is in here, which I have just marked, then what happens that when image is acquired, which is a nadir viewing image, then that image will suffer from FTPP if image belongs to a hilly terrain. Because if image belongs to a flat terrain like Indo-Gangetic plain or deserts where shadows are minimum, then you will not see FTPP. So, the main reason of this FTPP phenomena is because of shadows. In a hilly terrains, shadows are sometimes very large and they can give a depth perception quite easily. So, basically one myth which used to be there earlier, that a single image cannot give you depth perception, which is not true, which we have seen in part 1, that I have shown through several examples, not only images of the earth, but also on moon, that these images suffer from FTPP, and there is no reason that they are not giving depth perception. Of course, if they would not have been giving depth perception using a single image, then we will not have been or should not have been seeing FTPP. So, this myth was there earlier, that in order to see depth perception you need to have two images from two different angles, which is not now correct after identifying, recognizing this FTPP phenomena in satellite images of hilly terrain. So, when this sun object sensor relationship is there, which happens in case of typical remote sensing satellites, when in the morning hours, this is what. Now, one can argue that why can't have the sun on the northwest direction? That means the sun and the observer both are in the different hemisphere. See, the sun will set at the west before it reaches to northwest. It will never reach actually. So, it never reaches in the northwest direction, and therefore, evening hours data acquisition is not possible with this. So, of course, these orbits have been wisely designed and well tested. However, at that time probably FTPP phenomena was not realized for hilly terrain. Now, this is what I have been mentioning, that when this observer here and solar illumination in the same hemisphere, that is in the southern hemisphere, then we are bound to see FTPP. When we rotate by 180 degree image, then the solar illumination or we have shifted here the position of the observer, or we say by rotating 180 degree we can also shift the illumination angle also, or azimuth, sun azimuth. And when we put observer and illumination source in opposite hemisphere, then we will not see FTPP. So, when we rotate the image, this is what has happened, that both goes in opposite hemisphere and then FTPP is gone. Now, what are the methods of corrections One method which I have already discussed is the image rotation by 180 degree, which is very easy. Physically or digitally it can be done very easily. But as I have also mentioned that when we use satellite images and their products with other data sets in GIS platform or in Geographic Information System platform, then we are having problem. If we rotate, then everything has to be rotated, and that will create hell of problems. So, in order to avoid those things, we need to have some other technique in which we should not rotate the image, but still get rid of FTTP. And one technique which has come up, which was developed by ourselves, and that is the SRM, that is the shaded relief model based correction technique. SRM are also called hillshade. In literature you may find shaded relief model, or in somewhere for the same concept you may find a different terminology which is hillshade. So, what is this? Basically there is a product which is called digital elevation model. Lot of digital elevation models of different spatial resolutions of entire globe nowadays available for free download. Now, by using these digital elevation model, one can give a shadow or illumination source and through a modeling, and then we can create a different surface which is called shaded relief model, or different model which is called. So, the original many of these freely downloadable digital elevation models have been created using remote sensing images. So, first the remote sensing data, that those data sets have been used either using SAR interferometry technique or using stereo pair technique, and using either of these techniques a shaded digital elevation models of the globe has been developed of different resolutions, and these DMs we can use to create a hillshade or shaded relief model of our choice. Our choice means that illumination source and illumination angle, that is the sun azimuth and sun elevation angle during this modeling creating from DM to SRM can be changed as per our requirements. And then we can use some image processing, simple image processing techniques or transformation, color transformation technique to create a FTTP corrected image without rotating by 180 degree. So, the example we will be seeing soon. Now, the third possibility which we have also developed is creating image negatives. Rather than using a digital elevation model, then driving a shaded relief model of our choice, having appropriate sun azimuth and elevation, if we take a simple image, a false color composite or color composite image, and do some image processing techniques, perform some image processing technique, there too we can also get rid of FTTP. So, example from SRM and creating image negatives we are going to see now. When we go for SRM, though this flow chart may sound little complicated, but let me make things very simple. Basically, you need to have a shaded digital elevation model of almost same resolution, spatial resolution as of satellite image, which is suffering from FTTP. Now, when we use this digital elevation model, what we need to do? We need to create a shaded relief model which is having opposite solar azimuth compared to what satellite image is having. Because satellite image, it is having sun azimuth which is roughly in the southeast quadrant. But we want to create through this digital elevation model, hill shading modeling, we want to force the sun to go in the northwest quadrant, and that can be done very easily on a GIS platform or even on some image processing softwares like DAS. And when this is there, then what we need to do, that the color composite which we are having, we will split in 3 components, and this is what it is shown here, that it will be split in 3 components, and this is IHS, that is intensity, hue and saturation. This is what it is shown here, that a color composite image will be split it into 3 components using any standard digital image processing softwares, and now we will have 3 components IHS, intensity, hue and saturation. So, what is done in the next step is that intensity image is replaced by the SRM, which is having opposite sun azimuth as compared to FCC. So, now this SRM is replacing the intensity image, which we have split it from RGB, and remaining 2 components, that is hue and saturation, will go as it is. So, hue and saturation are going as it is, and once now we are having 3 components, I as SRM, which is having opposite angle to the satellite image, opposite sun azimuth angle, and then we are having same hue and same saturation. Now, in the last step is we combine or do the inverse transformation, that is from IHS to RGB. So, we started with RGB, we split it RGB into 3 components IHS. I of the image is dropped and it is replaced by SRM or shadow relief model, which is having opposite sun azimuth as compared to what satellite image is having. And when we do the reverse transformation, that is from IHS to RGB, we see an image which is not, which will not be suffering from FTTP corrected image without rotating the image by 180 degree. Let us see now. So, this is one image of Himalayan terrain, and in the center what you are seeing the Bhagirathi river, and as you can see that image is suffering from FTTP, and therefore, the Bhagirathi river is appearing to flow on the ridge, which geomorphologically, topographically it is impossible. Now, another point to note here, that what north is upward, and now if you see the sun azimuth, which is 163.3 degree, when you download a satellite image, you can also download the metadata of that image, particular image, and through metadata you can know when that image was acquired, what was the sun azimuth and sun elevation angle. Even if you have not getting that metadata file, there are models are available by which you can provide the center location in terms of latitude, longitude of your image or a study area, and the date on which the image was acquired. This much information is very much required. So, once you have provided these 2 information, that is the location, center location of the image and the date of the image, again you can drive this sun azimuth and sun elevation angle. But if you are having metadata, then wonderful, that will be give you more accurate information. So, here when this image from IRS, our Indian remote sensing satellite LIS-3 sensor, when it was acquired in the on the 12th October 1998, at that moment the sun azimuth was at 163.3 degree, and when this situation was there, the image is suffering from FTTP. Now, what as I have discussed through that flow chart, that using digital elevation model of the same area and almost of the same spatial resolution, a shaded relief model has been created. So, if you add 180 degree to 163.3 degree, this is what you will end up with 343.3 degree. That means the sun azimuth in this image is roughly here in the southeast quadrant, has been modeled or shifted through this modeling in the northwest quadrant by adding 180 degree. And now the sun elevation has been kept as it is. There is no change in the sun elevation, 49.2 in the original image. So, in my shaded relief model it is the same. So, we have played only with the sun azimuth. We have forced the sun to eliminate that area from the northwest direction rather than from southeast direction. And when we have forced like this, now you can see that the Bhagirathi river has gone in the valley. That means it is giving us a correct perception. So, but this becomes, this image, this SRM becomes our intensity image. So, what is done as I also explained through that flow chart, this is colored image, that is the RGB image. So, this image is split into three components I, H, S. I intensity image, H is hue, that is colors, and S is the saturation about the colors. So, three components are there. One component that I, original I of the image is dropped and it is replaced with this one which we are seeing, that is the shaded relief model having opposite sun azimuth angle. And two component, that is hue and saturation, remain same. And then when we perform the backward transformation, that means from IHS to RGB, this is what we get. Now here the sun azimuth, in real situation it is not possible, because as I have already mentioned that when we need sun to illuminate the terrain from northwest direction, which is impossible, because before the sun reaches could reach there, it will set in the west. So, it will never reach in the northwest direction, but we can model it, and this is what exactly it has been done in this case, that we have modeled the sun to go in the northwest direction and illuminate the terrain. And when observe, and what you would notice, that we have not rotated north here, or we have not rotated the image, north remained upward. So, that means this image can then be used along with other data sets on a GIS platform. So, this correction which you have just observed is without rotating, but employing a shaded relief model of opposite sun azimuth and then getting rid of FTTP, and this is what exactly has happened. Though there are, because none technique is universal, and here also we are having some artifacts which you are seeing in very bright blue color, because of in the original image these areas are where in the complete shadow, and as you can also observe here that these areas are in the complete shadow. So, when the areas are in complete shadow, in this FTTP corrected image, these might appear as artifacts, otherwise everything is in order, and which is without rotating we got rid of FTTP in this image. Now, the problem with this technique, one is of course artifacts. In this example you are seeing, some examples you may not see. If terrain is not so rugged, then these problem you might not observe. The other problem is all the time you require a corresponding digital elevation model, corresponding I mean of almost same spatial resolution, and that may create problem, because now we are moving from relatively coarser spatial resolution images to very high spatial resolution images of 1 meter or 60 centimeter. So, corresponding digital elevation model at the same resolution as satellite image are not available, and therefore, this technique cannot be employed for those images which are having high spatial resolution. So, this is one limitation is there with this technique. One more example of this technique we will see, and there is again of the Himalayan terrain. You are seeing again Bhagirathi river which is flowing here like this, and this is of course false color composite from our own satellite IRS 1D list 3. The sun elevation and sun azimuth, the important point to note here is the sun azimuth is there. So, this is the digital elevation model, and this is the shaded relief model derived from digital elevation model, where the sun, the azimuth has been the sun has been forced to illuminate the terrain from northwest direction. That means what the original image has 162, 180 has been added, and we end up with 342.5. And when this is the situation, and then same replacing this with the intensity image, and hue and saturation image remains same, backward transformation from IHS to RGB, and we end up with this image. So, north in this image, north is upward, no issue about that, and river has gone into the valley, that means the FTTP has gone, and this image or their products can, or its product can be used with other data sets without rotating the image. That is the underlying point, that here we are not rotating the image, but still getting rid of FTPP. All three things together. This is the input image which is suffering from FTP. Of course, this is color composite, false color composite. This is the shaded relief model having solar illumination from the northwest direction, whereas in the original image the sun azimuth is in the southeast direction. And when we do this transformation, what we having the sun here in the northwest direction, observer and north is upward, but still we are not having FTPP in this image. Now, one more technique which I would like to bring here is about the negative, creating negative of intensity image. And in this technique, we do not require a corresponding shaded relief model. That is the advantage, because in the earlier one, the problem which we started facing when we start using high spatial resolution images and corresponding digital elevation models of that resolutions becomes difficult to acquire. So, therefore, some other technique should have been developed. This is what we have done it, that a color composite, false color composite is RGB, a typical RGB image. So, what we can do, we can split that RGB into three different channels. We have, when we have been discussing this color space, we have discussed that within color cube, we can use various planes to project our image or data. A typical one is the RGB, and that is red, green, blue. Another one can be IHS, that is intensity, hue, saturation. Another plane in which we can project the data is CMY, that is cyan, magenta, yellow, which printing devices uses. So, within color cube, lot of maneuverability is there, lot of play can be done, and we can take the benefit and can get rid of such phenomena like FTPP. So, RGB is splitted into a color image is split into three component, that is IHS, and here what it is done, that intensity, negative of intensity image is created. And when we create a negative of intensity image, what we are doing basically, we are forcing the sun to go from southeast quadrant to northwest quadrant. And once it is done, then a backward image transformation, that means from IHS to RGB is done. So, intensity component in the negative of intensity image of original RGB, then hue and saturation will remain same as in earlier technique. And once it is done, then we get rid of FTPP without implying a digital elevation model or a shaded relief model. So, very quickly, without using much software or depending on the software or depending on the shaded relief model of corresponding spatial resolution, we can just get rid of FTPP, and that too without rotating the image. So, this is the latest development which we did a few years back, that getting rid of FTPP without rotating and without implying a shaded relief model. However, again the areas in the original image which has in complete shadow are giving some artifacts and some color variations as compared to original FCC. Otherwise, FTPP has gone, and still reliable interpretations can be done, because if we are seeing any image which is suffering from FTPP, that means inverse topography, then we are bound to make wrong interpretations. So, it is always required whenever we are using images of a hilly terrain that first get rid of FTPP by any of these techniques and then start doing interpretation. And one should not perform interpretation of images of hilly terrain without getting rid of FTPP. Otherwise, wrong interpretation will be done, and if those derivatives of interpretations are being used for other analysis, then the analysis may also create wrong results. So, these users of satellite images of hilly terrain must be aware that a phenomena exists which is false topographic perception phenomena. Three techniques which we have developed, depending on your requirements, one can use those techniques and can get rid of FTPP before starting analyzing or interpreting your satellite image. And the same image, the input image on the left side which is suffering from FTPP, on the right side you are seeing the image which has got rid of FTPP without rotating and without employing a shaded relief model. So, resolution, a spatial resolution issue will never arise in such kind of FTPP correction technique. This is the exercise which I got it done through students, and very interesting that the image was used when I gave this to students when image was suffering from FTPP, and they did the interpretation of lineaments, and then I got rid of FTPP and asked them to do interpretations again. And what you observe, which you can also see through this rows diagram, that the directions have completely changed of different features, and this here this northeast southwest direction features which were not so prominent in the interpretation were highlighted in the images which were FTPP corrected. So, this is what I wanted to demonstrate, that if an image is suffering from FTPP, one is bound to make wrong interpretations, and therefore, it is very much required to first correct FTPP. Image should be corrected for FTPP and then interpretation should be done. This is also lineament interpretation on corrected FCC also, it is there. Now, two more things I am going to show to you. The role of how this what I have done, that I have developed a simulated animation. Simulated animation means there are 8 scenarios which has put in a sequence with some time gap, and also position of the sun. So, when this animation starts, what you would see that the sun is rotating, and when the sun is in the southern hemisphere, observer is also in the southern hemisphere, you would observe FTPP. When sun goes in the northern hemisphere, observer remain in the southern hemisphere, you would not observe FTPP. So, now we will be seeing this image animation, as I have just explained that here the position of the sun is changing, and when we see the sun changes its position, the depth perception also changes, and at the same time we will also be seeing how FTPP appears and disappears. So, let us have this animation. What we are seeing, when the sun is in the southern hemisphere, we are seeing FTPP, but when sun goes in the northern hemisphere, we do not see FTPP. So, how this image has been created, or this animation, let me explain that 8 scenarios, north, south, east, west, and northeast, southeast, southwest and northwest, 8 scenarios were created using that shaded relief model of 8 different locations of the sun or sun azimuth, and then backward transformation. So, 8 times the topographic corrections or FTPP has been done, and so 4 times what you are seeing in this, when the sun is in the southern hemisphere, though this is white and in the background is black, one might say this is moon, but it is believed this is the position of the sun which we are showing here. So, when the sun goes in the southern hemisphere, we are observing FTPP. When sun goes in the northern hemisphere, we do not observe FTPP. Please note that we have just changed the sun azimuth, not the sun elevation angle. So, here now as soon as now sun is gone in the northern hemisphere and observer in the southern hemisphere, we do not see FTPP. So, when both observer and sun are in opposite hemisphere like this currently, then we are not seeing. Now, we are seeing FTPP, and when it goes again, see, it is we are not observing FTPP. So, this further explains that what is the role of sun azimuth in case of FTPP, and this clearly demonstrate that FTPP occurs when the sun azimuth or the solar illumination or illumination source and the observer are in the same hemisphere. When they are in opposite hemisphere, we will not be seeing FTPP as being demonstrated through this animation. Now, we are going to observe another animation in which instead of creating simulated images for the sun azimuth, in this animation, the sun azimuth has been kept same, that is in the northwest direction without FTPP, and FTPP corrected images, and every 5 degree starting from horizon, successive images has been created and put in a animation. So, that is why I use the word simulated animation. So, in this simulated animation, what you are seeing, when sun is the near horizon, you see very darkness in the image, shadows are very large, and therefore the depth perception is the maximum when the sun is near horizon, that is 5 degree or 10 degree. When sun goes overhead, the shadows becomes minimum and depth perception reduces significantly. So, this demonstrates that how sun elevation also plays role for the depth perception, and also it cancel that myth which says that for seeing a depth perception in satellite image, one require images from 2 different directions. That is not correct in that way. So, here one can see that how sun elevation angle plays very important role. Why I am discussing this animation here? Because during winter season, and this is the situation, in winter season the sun is in the low horizons or near horizon in the early morning when images are being acquired, and therefore if you doing some analysis of having images of winter season and summer season, then you will face this problem of different shadow conditions. So, one should be aware, though through modeling using different shadow relief models, one can correct one image and then another image can be used for comparison. But when 2 images of 2 different seasons are being used for certain purposes, one must be aware that because of sun elevation angle, they might be having different shadows and therefore different shadow conditions and depth perception, and the same with the sun azimuth also. So, this one has to keep in mind when we are using satellite images, and especially I am talking about hilly terrain, because most challenging is using satellite images of hilly terrain like Himalaya, which is highly rugged. This example is also from Himalaya of Bhagirathi river valley, which is a part of or a tributary of Ganges. Now, what we see that once we published our work about and identified this FTTP phenomena, people started using our work, and they have started incorporating in their publications and also started developing their own thing. Though here this Wu et al. Have mentioned in their paper that FTTP is a relief inversion problem and firstly identified by Saraf et al. In 1996. So, there is a clear cut acknowledgement, though this should have been updated here that it is not anymore in press. This paper has already been published. Anyway, so we what they have done, they have employed wavelet transformation, which is a very strong or very powerful technique in image processing, and they have taken image of moon surface and also a digital elevation model, and using that digital elevation model and opposite direction shadow relief model which was created in the middle row, middle column, and then this same way the transformation is done. So, when this is done, then through this wavelet transformation, you see without rotation FTTP has gone on the right image. See, the compare with the left image, extreme left image and right image of the same area, but the left image is suffering when north is upward, left image is suffering from FTTP. When you see when using this shadow relief model and through a wavelet transformation, then what you see that FTTP has gone without rotating the image. In this technique, Wu et al. Have used the shaded relief model of opposite direction. Another example also shown about the crater of moon surface, and then shaded relief model of the same area in the middle, bottom middle, and then on the right bottom image, which is now does not suffer from FTPP without rotating, that has been corrected. But there is a limitation in their work. The examples which I have shown from colored images or false color composite or RGB images, here very cleverly what they have done, they have taken only black and white images. So, there are no three components, and therefore, the artifacts which I have mentioned in my correction technique, the problem of artifacts will not arise here, because it is a single channel image or single band image. But nonetheless, a technique was developed, and which is based on the wavelet transformation, and FTPP has been corrected. Once it has been corrected for one band, it can be employed to correct for other channels or other bands, and then finally a color composite can also be created. So, likewise this FTPP phenomena which we have discussed, the causes of FTPP, what are the reasons which are causing the FTPP, and where these are occurring in a hilly terrain, rugged terrain, and not only on the surface of the earth, but also on the moon, and also FTPP is observed on the surface of the Mars, and you can check also on the Google Mars. So, when you install Google Earth, and the same time Google Moon and Google Mars are also installed, and there also you can observe on the left image, like here, this is Mars Express, the crater area, and on the left image it is suffering from FTPP because sun azimuth is from the southeast direction, and therefore you are seeing the crater not in correct perception. But in this when I rotated this image by 180 degree, then we start seeing things in correct perception. So, that means what we can say after seeing one more example of surface of the Mars, satellite images of surface of the Mars, which is having also some ruggedness, and that what we can say here with a lot of confidence, that images acquired by polar orbiting satellites or sun synchronous satellites of hilly terrain, not only of Earth, Moon or Mars, will always suffer from FTPP. This is a strong and bold statement which I have made, that images of a hilly terrain acquired from polar orbiting satellites of any part of the globe or Moon or Mars will always suffer from FTPP. That means we can say that FTPP is a universal phenomena, and for of course for hilly terrain, and anybody who started or who uses these images of hilly terrain of any of these bodies, Earth, Moon or Mars, planet or satellites, then one should be aware about the phenomena. One should, whenever using, one should make corrections and then start doing the interpretations. One more example is here of Mars surface, Arima crater. Again the same scenario is here. Very interestingly, that is why in the part 1 I have said that it is going to be entertaining. So, this is what I am going to show, the entertaining. And there is a artist whose name is Holdsworth. What he has identified this phenomena much later, of course, and what he has started putting his own gallery, which is called Holdsworth, Pippi Holdsworth Gallery. And what he has done, that taken one image which is suffering from FTPP, and then part of that image, the rotated image, and then created a collage like here which you are seeing, or like here which you can see again from the same Dan Holdsworth, and also mention the forms FTP, that is false topographic perception. So, on the left image which is suffering from FTPP, and then right image which is just rotated off by 180 degree of first image is not suffering from FTPP. So, even artists too have exploited this FTPP for their own benefits. You remember that simple engraving or hatching features can create depth perception, and that was developed by artists. So, this FTPP is now going back to artists again through these satellite images and showing this thing. One more example here is like in the book, a very famous book, Image Interpretations in Geology by Steve Drury, and here what he has mentioned about this crater, that view this up image is clearly that a crater with a central peak. Viewed from top of the page, the image should flip from reality to an inverted relief. So, if it is rotated by 180 degree, that means forcing the sun to go in the northwest quadrant, then you do not see FTPP. This is what it is demonstrated in this book. So, people have after our publication and later work on corrections, people have started accepting that FTPP phenomena exist in the satellite images of hilly terrain, whether images are of Earth, Moon or Mars, and also now it is part of the literature. So, this is about the images in the FTPP in the satellite images. One more small thing which I want to show you, because in satellite images the depth perception or FTPP is occurring because of shadow and contrast. The shadow creates the contrast between two adjacent objects, one is illuminated, one is in shadow, and when this situation comes, a completely different perception is developed, and this is what it is demonstrated here, that I am going to show this checker blocks, and there are two blocks which has one is marked with A, another one is marked B. And if I say that these blocks where A and B are marked and these letters are written, both are having same shade of grade, no one would believe. But exactly this is what happened in case of satellite images too. So, what I am going to demonstrate here is slowly one by one I will hide everything except leave these two blocks and two square, if I can call A and B, and see that whether difference in the shades exist or disappear. So, let us have a closer view on A and B. Keep watching, and slowly I am hiding the remaining areas except A and B, and see now they are, see A and B are having the same shade. So, now what is the basically reason? Let us go back and see again, observe again whether the difference is created when we start removing these parts from there. Now, again they are having, the reason is because of the surroundings, the neighborhood. Basically this is what exactly happens in case of satellite images. Here there is no question of say depth, but what I am trying to demonstrate, when then two contrasting things are in adjacent position in neighborhood, then our perception changes, and this is what happens in case of satellite images of hilly terrain. Here like a block A or this square A is surrounded by lighter parts, and therefore it is appearing as darker. And whereas opposite to contrary to this, the B block or B square is surrounded by darker, and in relative terms it is appearing as it is we are perceiving as a relatively brighter as compared to surrounding squares. So, when we start hiding, what is happening? We are hiding the surroundings, and when the surroundings are hidden, then we do not see any difference between them. So, in absolute terms they are having the same shade, but because of surrounding we are getting the wrong perception. So, this is what also happens in case of satellite images, when I say that even a single image of a hilly terrain can give you depth perception because of the shadow, and shadow creates the contrast with the surroundings, and a completely different perception. And this is what is basically that if I draw a connecting bar between these two, what we see that they are having the almost same shade. And because the bar is having the same shade, and both there is when the bar part comes in the B, we do not see any boundary. When bar part goes in the A, we do not see any boundary again. So the point which I was trying to mention is A and B are having the same shade of gray. However, the surroundings of both A square and B square are different, and therefore their appearance is completely different. So this perception, and this is why we gave this name, the false topographic perception phenomena, because this is the shadows is creating a completely different perception in our brain, and therefore we are seeing FTPP. Even if you see the some softwares in which which allows us to create a shaded relief model, this is example from ArcGIS. Whenever you go for creating a hillside, which is here like a hillside, automatically the values which will come about the azimuth is always azimuth angle will come always from the north or from this direction. In the default, the softwares have been set like this. See here 315, 45, not near 145 or something. So the developers of the software have kept the default value while creating hillside, that the illumination source should come or should be located in the northwest direction, without basically accepting or acknowledging the false topographic perception phenomena. One more example is here, that sun azimuth, when you are having a 315 degree, this is what you see the terrain, but when I change, that means the illumination source is here, that same terrain looks completely opposite. And this is the point which I was mentioning, that when the observer and the solar illumination source is in the same hemisphere, one is bound to see FTPP, like here in this one we are seeing. So this brings to the end of this discussion. For me it has been very interesting, and through this work we have published a series of papers, 4 papers so far, and about this identifying false topographic perception phenomena, then different correction techniques, and also paper on the moon surface observed that FTPP was observed there. So this brings to the end of this part 2 of false topographic perception phenomena. Thank you very much.